Imagine throwing a tennis ball at a brick wall. It bounces back, always. That's how we expect the world to work. Solid objects meet resistance and the laws of physics seem unbreakable in our daily lives. Solid objects don't pass through each other. That's our everyday reality. A rule so fundamental that we rarely question it. It's the reason we trust the ground beneath our feet and the walls around us. But in the quantum world, this rule is spectacularly broken. The universe at its smallest scales plays by a different set of rules, ones that defy our intuition. Sometimes, a particle like an electron can simply appear on the other side of a barrier, as if by magic. It's as though the wall simply ceases to exist for a fleeting moment. This is quantum tunneling, a phenomenon that's baffled physicists for over a century. It's one of the strangest and most fascinating effects in all of science. Electrons can tunnel through barriers they shouldn't be able to cross, defying classical physics. The rules we know simply don't apply at this scale. It's like a car with no gas appearing on the other side of a mountain, an impossible journey made possible by the bizarre nature of quantum mechanics. For years, we could only calculate the odds, never see the journey itself. The path of the electron was hidden, a mystery locked away by the limits of our technology. The process was a black box, a forbidden zone. No one could peer inside to witness what truly happened as the electron tunneled through. On August 16, 2025, scientists have finally witnessed what happens inside the electron's tunnel. For the first time, the invisible became visible. We've seen the ghost in the wall, turning a century-old mystery into a new chapter of discovery. The impossible has become observable, and the unknown a little less mysterious. This breakthrough redefines what we can know about the universe, opening doors to new questions and possibilities that were once beyond our reach. To truly grasp quantum tunneling, you have to shrink your perspective down to the subatomic world, where the rules of everyday life no longer apply. Here, the universe behaves in ways that seem almost magical to us. In this strange realm, particles like electrons aren't just tiny points darting around. They're also waves of probability, spreading out like ripples across a pond, existing in many places at once until measured. When an electron's wave encounters an energy barrier, a kind of invisible hill it shouldn't have the energy to cross, most of its wave reflects back, as if bouncing off a wall. But quantum mechanics allows for a strange twist. A faint part of the wave leaks through the barrier, creating a small but real chance the electron will suddenly appear on the other side, as if it is teleported. That's quantum tunneling. The particle's existence stretches into regions that should be forbidden, making the seemingly impossible not just possible but inevitable over time. This isn't just a wild theory. Quantum tunneling is a real phenomenon that powers the sun, enabling nuclear fusion to occur at its core, and is essential for life as we know it. For decades, scientists could only observe the start and end points of tunneling events, while the journey through the barrier itself remained a complete mystery. What really happened inside the tunnel? Did the electron simply vanish and reappear, or was there more to the story? How long did the electron spend inside the barrier? Was it instantaneous, or did it take a measurable amount of time? And did the electron even have a definite position while it was inside, or was it smeared out, existing everywhere and nowhere at once? It was like watching a movie with the entire middle section cut out, leaving us to guess what happened in between. We could see the before and after, but the heart of the process remained hidden in darkness. Now, new experiments are finally beginning to illuminate what happens during quantum tunneling, opening a window into one of nature's deepest mysteries. Quantum tunneling's story is filled with legendary physicists. In the 1920s, Friedrich Hund and George Gamow revealed tunneling's role in radioactive decay, particles escaping the atom by tunneling out. The idea was so strange it sparked fierce debate. Einstein, skeptical of quantum randomness, found tunneling unsettling. Schrödinger's wave equation predicted tunneling, but its meaning was unclear, leading to famous thought experiments like Schrödinger's cat. The particles seemed to be in a superposition, both reflected and transmitted, until measured. For decades, the debate raged. Did the particle travel faster than light? What was its journey like? Without direct observation, scientists were left with only hints and paradoxes. The true nature of the tunneling journey remained elusive. For a century, the electron's journey through the tunnel was invisible, too fast to capture. The breakthrough came with the Clock, a revolutionary experiment using light as a stopwatch. At the Max Planck Institute, scientists fired ultra-short circularly polarized laser pulses at atoms. The rotating laser field acted as a clock, marking the moment an electron tunneled out. By measuring the angle of the escaping electron, they could pinpoint when it emerged. This allowed them to measure the tunneling event with attosecond precision. The results? The electron spends a real, measurable, though incredibly brief time inside the barrier. Exotic theories of instantaneous travel were ruled out. For the first time, we have direct empirical data from inside the quantum tunnel. The forbidden zone is no longer hidden. Solving the tunneling mystery is a triumph, but its impact goes far beyond physics. It opens up new possibilities in various fields of technology and science. For years, we used tunneling in technology without fully understanding it, like driving without knowing the engine. This breakthrough changes everything. Now we can fine-tune the quantum engine, leading to innovations we once only dreamed of. In electronics, tunneling limits how small and fast we can make computer chips. This understanding allows us to push those boundaries further. Understanding tunneling time lets engineers design better, more efficient transistors, enhancing the performance of our devices. Solar panels and medical imaging also rely on tunneling. This knowledge can lead to significant improvements in these technologies. Optimizing these processes could boost solar efficiency and revolutionize atomic-scale imaging, making them more effective and reliable. With this knowledge, we gain new control over the quantum world, opening doors to unprecedented technological advancements. We can design quantum switches operating at attosecond speeds, opening the door to faster computers and ultra-sensitive sensors, transforming how we interact with technology. The ability to time and manipulate tunneling events could launch a new era in materials science and quantum computing, leading to breakthroughs we can't yet imagine. The mystery has become a tool. The future is quantum, and the possibilities are endless. For ages we've dreamed of walking through walls, a staple of science fiction. With proof that electrons spend real time inside barriers, this fantasy feels a bit closer to reality. Of course, people won't phase through walls, quantum rules don't scale up to our world. But the discovery that tunneling is a real measurable journey makes reality more fluid than we imagined. Science fiction lets us explore the consequences of breakthroughs before they happen. Now science shows that a version of phasing happens constantly at the quantum scale. The universe is as strange as our wildest stories. As we peer into the tunnel, we open new frontiers, reminding us that the quantum adventure is just beginning.